All right, so this is the physics test review for chapter, what, 16 through 19? That's not a CH, oh well. 16 through 19. First question, proton lady and proton man really hate each other. How much force does the mayor of Nucleotropolis have to apply to make them meet each other and reconcile their differences at a distance of 1.3 micrometers? You tell us Mr. Welch question because there's a whole bunch of nonsense in there. But what you need to know is it's proton lady for a reason, and proton man, again, for a reason. They're protons, okay? Hidden in the name of the person is the name of the charge, or the amount of charge, which means Q1 is 1.602 E negative 19 coulombs, and that's also Q2. They're both protons. Naturally, okay, when you have two likes, two positives together, they want to push away from each other. Hence the question. Mayor Nucleotropolis is going to apply some force. Okay, well, we're going to apply some force to push these two together, and we want them to be at a distance of 1.3 micrometers. I think was the number. And so we grab Coulomb's law, which tells us about point charges and the force between them, force of attraction or repulsion. The force is going to equal K, Q1, Q2, all over the radius or the distance between them squared. So as we go through and make this calculation, a couple of things. K is a constant 8.988 E9. We multiply that by the charge, which is 1.602 E negative 19. If one of them is positive and one of them is negative, the negative nature of the force just tells us that they're going to attract each other. Positive total makes it push away from each other. I can write that twice, or I can just square it. Divided by the radius, 1.3. You really do need to know your prefixes. Micro, that funny looking M, is an E negative 6, and that also gets squared. Okay. Keep in mind, the square on this was only because Q1 equals Q2. If the charges are different, then we're going to have two different multiplies there, right? All right, so grab our calculator, throw it in the calculator. 8.988 E9 times 1.602 E negative 19. I'm just going to do it again, times 1.602 E negative 19. I like to hit enter, divide by, and I'll put parentheses around this. You don't really need it with the scientific notation, but Mr. Welch has his habits. Negative 6, close parentheses, squared. And we get 1.36 E negative 16. It's a force. That should be in newtons. So we have 1.36 E negative 16 newtons. Not a lot of force, but remember, protons and electrons, they're so microscopic and small in their mass that if we pushed with any real big force, they go flying. Okay? When you breathe, I mean, you're pushing atoms around like nothing. Okay, so it's a similar idea there. Okay, question number 2. I want to set up an electric field of 1600 newtons per coulomb between two plates. If I hook up to an 8.2 volt battery, how close do they need to be? Now here's the fundamental idea that you have to understand. Electric fields can be measured a lot of different ways. Okay, the formulas for the electric field, there's actually like 3 of them. Okay, so we kind of have to look at what are the different ways we measure electric fields. I think one of them is KQ over R. That's the electric field a certain distance away from a point charge. Yeah?
Isn't it R squared?
Thank you. I'm trying to go off of memorization and I don't have them all memorized. So if you see any other errors, let me know. There's also a formula that would end up looking like F over Q. I think the formula was F equals EQ, but if you rearrange, you get E equals F over Q, where it's how much force do you have to apply to keep a charge where it is, or how much force is being pushed on a charge because of an electric field. And the last one is the electric field is the voltage difference divided by distance. Okay, you might have seen V equals E times D. There are different variations of this formula, but they all calculate to the same thing. How strong is the electric field between two things? When we look at the other measurements that we're given, so our E in either case is 1600. It uses newtons per coulomb, but you could use volts per meter just as easily. They have the same unit, same value. Okay? But if I look at what else is given to me, I'm told that I have 8.2 volts between two plates. Okay? They're hooked up to a battery. Okay? You hook it up to your 8.2 volt battery. I want the electric field, okay, set up in there. The question is, how far apart? Well, if I'm looking at distance between, and we have a voltage set up, that tells me that I'm going to be using this bottom version. That does not mean on the test that it's automatically going to be that version. You might have to look at it and make some analysis. So be prepared to read through the question, look for what you have to work with. But electric fields can be found through a myriad of different ways. In this case, we have 1600. It's going to equal our voltage of 8.2 over D. And I just taught this the other day in my Algebra 2 classes. What's that called? The old Welcheroo. We did the old Welcheroo to get D equals 8.2 over 1600. And what is the distance between the two plates? Got your calculators. 8.2 divided by 1600 comes out to 0.0051. So for the sake of just units, I'm going to go to 5.1 millimeters. If you write 0.0051 meters, it's not wrong. When it's a nice thing like millimeters or centimeters, I like to move it. Not a requirement. Okay, question number 3. We have a capacitor that is 2.7 microfarads. And I'm going to hook it up to a voltage or a battery source of 6.3 volts. And I want to know how much charge. Now this is one of those things you have to fundamentally understand. When you see the word charge, you have to realize that we're talking about Q. Whether it's a little q or a big Q just depends on, is it a compilation of charge or is it an individual charge? Obviously, we're going to pile up a bunch of little charges, so we're going to end up with a big Q. There's a very simple formula for capacitance with charge and voltage, and it is that Q equals CV. Well, this is going to be just a straightforward plug in and be done. The charge built up on the capacitor will be 2.7 E negative 6 for our capacitor times our voltage of 6.3. Pretty straightforward calculation. 2.7 E negative 6 times 6.3. And we get 1.7 E negative 5. Q equals 1.7 E negative 5, and charge is always measured in coulombs. So this is one of those where it gets kind of funny, because capital C is capacitance measured in farads, capital Q is charge measured in coulombs. There's a lot of C's and stuff floating around. Try to keep track of which one's which. But that's it for that. Question number 4, more capacitance stuff. I've got a capacitor. I've got a capacitor with 5.1 microfarads, and I want it to hold an energy. Since I'm wanting it to hold energy, that should make you think of potential energy. Potential energy being 11. And this one, I don't know why it confuses people, but it happens to. A little m in front of a unit is milli, which is just E negative 3. Okay? Joules. That's how much potential energy I want to store in there. And the question is, how much voltage do I have to get attached to it in order to apply that. We did this with the defibrillator. It's a big capacitor with a discharge. This is very similar. The formulas for potential energy in a capacitor, there are different variations of it, but the one that's the default is 1/2 CV squared. Now, keep in mind, with Q equals CV, I could give you things like the charge and the voltage, not give you the capacitance, and you could go and dig out the capacitance or rewrite this formula. But with this version of it, we have 11e negative 3 equals 1/2 5.1 e negative 6 times v squared. To solve that, we're just going to take our 11 e negative 3 times it by 2, that gets rid of the half, and we're going to divide it by 5.1 e negative 6. Gives us 4,313. That is not the correct voltage because it's still a v squared, so we have to square root that. And when we do, we end up with 65.7, so we'll go to 66 volts. Is what we'd have to hook that up to. That is a lot of voltage, depending on what you're doing with, what energy source you're working with. You know, we have 120 in the wall, but typically when we're doing capacitors, we might be working with a smaller voltage, so that's actually pretty big. All right, question number 5. Okay, I have 2,200,000 electrons. Okay, and they're set up on a capacitor. Okay, so imagine they're on a capacitor. Boop. Okay, a bunch of these negatives sitting here. Okay, all right. I'm going to release them through a circuit. Okay, they're going to go in and power some light bulb or something. And I notice. Okay, we're going to just kind of measure through this space here. So they go through a section of wire. That's a really bad looking arrow. They go through that section of wire in 1.3 milliseconds. Okay. We're going to go through that little section of wire. I notice all 2,200,000 of them go through in 1.3 milliseconds. And the question is, what's the current? Current in its most pure definition. That's what this question is asking about. Current in its definitive form is the movement of charge over time. It's how fast is charge moving through a space in the wire. Okay, it's the flow rate of charge. Well, the first question is how much charge? I have 2,200,000 electrons, but each electron has its own charge. So to find the total charge that's moving through there, I need 2,200,000 times the charge of each electron, 1.602 e negative 19. Now technically the charge of an electron is negative, but I'm not concerned about the direction of charge flow. I just want to know how much is flowing. And I'm going to divide that by the amount of time, which is 1.3 milli, means e negative 3. If I do that divided by that, I should get my charge, or my current, or the rate at which my current is flowing. So 2,200,000 times 1.602 e negative 19 divided by 1.3 e negative 3 comes out to be 2.7 e negative 10. 2.7 e negative 10 amps. The reason I like this question so much is it puts into perspective just how much charge has to be flowing. Okay, when we talk about electrons moving, 2 million of them is not a lot in terms of producing that charge. Not if it's moving in 1.3 milliseconds, which by the way seems crazy fast. This stuff has to be moving extremely fast and in extremely large quantities to be able to get a significant current flow. All right, we turn the page, we're going to chapter number 6, or question number 6. I've got a 1900 ohm resistor and it's a power rating of 15 watts. I've got a resistor that's 1900 ohms. It has a power rating of 13 watts. That means if I go above 13 watts, there's a chance I'll burn it out. Like some students the other day almost did with a motor, because they decided to apply a little too much power and try to make the thing light on fire. You know who you are. Yes. Question is, what is the max current and voltage that I can supply before I kill it, before I burn up the resistor? All right, and so we're just looking at what is the relationship between power, current, voltage, and resistance. We have two different definitions. P equals IV is the power formula. We also have Ohm's law, which is V equals IR. I don't have V or I, which means neither of these formulas on their own can be solved, because I have the same two unknowns in both formulas. However, if I do a substitution, and you guys might already have these written down, I can say that P is I squared times R, which means I can now find the maximum current I can supply before I burn it out by taking 13 times equals I squared times 1900. I'm going to divide that off. 13 divided by 1900, but that also has to be square rooted, which gives me 0.083. So my current max would be 0.083 amps, or 83 milliamps. Again, milliamps are a really common measurement for current. Then when I go to do the voltage, I want to acknowledge that that current that I have, 0.083, is a rounded number. Please don't use rounded numbers to make more calculations. Try to use your calculator. Technology's there for us. But if I just use V equals IR, 0.083 ... times the R, which was 1900. Okay, I'm going to take that times 1900 to get a voltage of about 157. So V equals 157 volts. You might get 160. Again, sig figs, we're way past the point of being really particular, but you know, the question had 2 sig figs everywhere. It should be 160 to be perfectly accurate. All right, so now we're on to question number 7, and we have a 320 ohm resistor, and we have a 650 ohm resistor. They're both light bulbs. I have 7.6 volts in some sort of a battery support, 7.6 volts, and I want to set them up to obtain the dimmest lights. You need to draw the diagram. Do not just say, put them in series or put them in parallel. So the first question is, if I want them to be dim, what do I want to do? Series or parallel?
Series.
Series is what will drop the current. Dropping the current drops the power. Okay, so the lower the light is going to come from a lower current. And so we are going to put them in series. There's my voltage, a resistor, another resistor. Your diagram does not have to look the same as mine, but it does need to look like a series circuit that is completed with a battery source. Okay, you've seen me draw enough of them. You should be able to piece together what they look like. You have models down below. So that's the setup. Okay, I'm going to tell you right now, it's not enough to be drawn. On the test, the question's going to ask you about things like what's the current and the total resistance in the circuit. So we need to go find a couple things out. How would I find the R total in this case? If they are in series, how do we add resistors? We just add them. Now, what if I asked you to get the brightest lights? How would this problem be different? We'd put them in parallel, and that's when we'd add them differently. So it depends on what I give you. Maybe I give you 3 resistors, and I give you some choices. In any case, our R total comes out to what, 970? by just adding the two resistors together. If I wanted the current, okay, I would take Ohm's law, I take my voltage divided by my resistance to get my total current. It's just one simple loop, okay? The voltage is 7.6 divided by 970. How much current is flowing through my circuit? You guys got a calculator? Let's get it ready.
0.0078.
So 0.0078 amps. Not a lot of current. You got a lot of resistance for a small battery. I mean, I just want you to understand, in this question, I'm going to ask probably for more than just a picture. I'm going to ask for things like, hey, what's your resistance total? What's your current total? Could we figure out how much voltage loss there is on each of these resistors by taking our current of 0.0078 and timesing it by the resistance to find the voltage drop? Now we could do that. So there's more that we might dig out of there. You just have to be prepared to say, I can find anything I want out about this circuit. You're going to see more of that in the next two questions. Well, the next few. All right, question number 8. We're going to do 8, and then we're actually going to jump to 10 because of the way the questions are worded. We got one there, and then a split to a single. And down here on the split, there's a double on the other side. All right. We've got 3, 2, 7, 5, 8, and 9 volts. Okay. Your first question, number 8, is to find the total resistance. Think of it in chunks. You have to break pieces down into simpler and simpler parts. So for instance, if I look for something that is the most buried in the sequence, I see that I've got this parallel branch, but I cannot add the parallel branches until I combine them into single items. So 7 and 5 can't be added to the 2 until they're added together. So what is 7 and 5 going to produce? 12. So now I have a 12. If you wanted to redraw the circuit, you sure could. You now have the 3, a branch with 2. There's my 8. So now I'd be at 3, 8, 2, and 12. Now I want to add another chunk. Well, the 2 and the 12 I could add together, but I can't add them in series. I have to add them in parallel. This is where we do the 1 over 2 plus 1 over 12 to the negative 1. And we use our calculator. 1 over 2 plus 1 over 12 to the negative 1. 1.71, which is what this.
Wait, how'd you put that in the calculator?
1 over 2 plus 1 over 12. You didn't have 12.
Oh, I didn't have the 12.
Yeah. Okay. Create the 1.71. Now they're all in series. So I can just add them up. Add 8, add 3. It's going to give me 12.71 ohms. Now, I want to make this clear. It is possible to add the whole circuit at once. But to do it would look like this. 3 plus, we have a parallel connection. So now we do the parentheses. 1 over 2 plus 1 over 5 plus 7. Because they're in series, they would add together like that. To the negative 1 plus 8. I mean, you could do it all at once. I'm a person who likes to break it down a piece at a time. But that's kind of where I go at it. Okay, so we're going to take this question. Now that we know the total resistance, we're actually going to take this question and go to question 10. Question 10 asks us to find the voltage loss across the 3 ohm resistor. Okay. Now I want to make this clear. In this problem, it's really easy to find the voltage loss. But I can ask for the voltage loss across any resistor I want. So I'm going to do this one, but I'm going to show you how to find it on every single one. All you have to do is multiply the resistance by the current that flows through it. Okay? So 3 times, we got to find the current. So we would take V over R to give us our current, right? Ohm's law, we divide the resistance over. It's 9 divided by 12.71. Our current that flows through the circuit should come out to be 0.07 or no, 0.708. 0.708 amps. Okay, you're going to have to find the current to answer the last question. Now I can use that current times any resistor it goes through to find the voltage loss. So if I times this by 0.708 times my resistance, right? I've got my R, I've got my I, V equals I times R. How much voltage loss do I have through the 3 ohm resistor? Just times that. Get it clear. We get 2.12. We'll call it 2.1 volts. Okay? That's the answer to question 10. It's 2.1 volts. However, I want to know that you can find it on every single resistor. Okay? The 8 ohm resistor, same thing. 0.708 amps goes through there. So how much voltage loss do we have here? 5.66?
Yeah.
5.66 volts. There are 2 ways to do this. I want to show you both options. If you find all the voltages everywhere else in the circuit, then no matter what path you choose, you have to use up the rest of the voltage. We know we've got, what, 9 volts? We've got 9 volts. We've used 5.66 and 2.1. We'll make this 5.7 just to round it off a little bit. That comes out to 7.8. I'm missing 1.2 volts. I know without doing any other calculations, I'm going to use 1.2 volts here. Now, how do I find it if I don't just make that assumption? The way we do it is with the equivalent number. The 1.71 is the number we would use on this component of the circuit. The 1.71 times 0.708 should give us roughly 1.2. Is that correct? Yeah, we get the 1.2. Now, guys, that tells me how much is going through the 2 ohm resistor. That does not tell me how much voltage loss I have at the 7 or at the 5. This is really getting pretty buried in the complication. But the way we would figure it out, I'm not saying this is how it's going to go on the test, but guys, how much current does I1 have to have in order for a 2 ohm resistor to produce 1.2 volts? It would be 0.6 amps. Okay, 0.6 amps is going that way. I have 0.708 amps, which means that 0.108 amps goes through the 2 resistors down here. And if you take 0.108 with your calculator times 7, we get 0.756. And if I do 0.108 times 5, if I add those together, I get roughly the same 1.2 volts. We can see how it works on each individual piece. Are you going to have to break it apart that far? Probably not. But this is physics. We should talk about how the problems are solved when they get more complicated. We shouldn't just, play around with the simplest versions of every problem. Okay. So there's a lot of options in how to break that down. Hopefully you're not too lost or confused, because if you are, that's too bad. Come and ask me your questions. Last question, number 9. I'm going to go back to a little bit simpler. You should see basically the exact same circuit, except that they're all capacitors. They use basically the same numbers, except they're in microcoulombs because that's a bit more realistic. But the actual pattern of the circuit is identical. Each of these is micro, so 3 microcoulombs, 2 microcoulombs, 7 microcoulombs, 5 microcoulombs, and 8 microcoulombs. We want to just add up the circuit, get our total capacitance. Same thing happens. We add from the most complex and work our way out of that. How do you add capacitors that are back-to-back like that, or in series? The capacitance for that will be 1 over 7e negative 6 plus 1 over 5e negative 6 to the negative 1. And we throw it in the calculator. 1 divided by 7e negative 6 plus 1 divided by 5e negative 6 to the negative 1. Give me 2.92. So 2.92 e negative 6. Okay. Now I want to add that to my 2. Those are in parallel. When we add in parallel with capacitors, we just add. So this bigger loop is now going to be 4.92 e negative 6 coulombs. I'm going to redraw the circuit just because I've got a lot going on. We have our 3 microcoulombs. Okay, we have condensed this series parallel combo to a single 4.92 e negative 6. And over here we have 8 e negative 6. That's my 9 volts. All right. The rest of these are all in series. I should just be able to add them. 1 over 3 e negative 6 plus 1 over 4.92 e negative 6 plus 1 over 8 e negative 6 to the negative 1. I'm going to go 1 over that. Whoops. It's supposed to be a 4 now. 4. Plus 1 over 3 e negative 6 plus 1 over 8 e negative 6. All of the negative 1 gives me 1.51 or 1.5 e negative 6. 1.5 microcoulombs. Dang it. And there we go.